Special relativity. A free object, like our particle, moves at a constant velocity. We assume that at time 0, the object was at the point where the origins coincide. With no net external forces, it must travel at its constant velocity. Its position must be a linear function of time in both frames of reference. So in the S' frame, if the object were to move inside of this frame, we would call this U'. And any motion it does inside that frame would have the position X' equals U' times T'. Its velocity and its change in time determine its position in that frame of reference. In the S frame, the motion of the object, which is pinned to the S' frame, moves at a speed of v. So it moves with the frame, and so we use v to mean the movement between frames. So in this case, the position of the object, according to the S frame, would be the velocity times time. So we have X' equals U', T', and X equals V times T. Our only guidelines are that the constant velocities in one frame should imply a constant velocity in the other frame, meaning according to the S frame, the S' frame is moving at V. However, according to the S' frame, it is the S frame which is moving at a constant velocity in the negative v direction. This gives us a linear transformation. X' can be written as some constant times the S frame's position plus some constant times the S frame's time. The same can be said about the T', which can be made up of c times x plus d times t. To determine the constants a, b, c, and d, so what we will do here is we will make these equation 1, and these will be equation 2. One. If the object were fixed at the origin of the frame S', it would move at a speed v relative to the frame S. So equations 1 would become X' equals, there's no motion in this frame, 0. But according to X, the change is v times t. Inserting these equations into equation 2, we get that X', which equals ax plus bt, becomes 0 equals avt plus bt. If we move a to the other side, and then we can divide both sides by t, and we are left with b equals negative av. 2. If the object were fixed at the origin of frame S, it would have a velocity of negative v according to someone in the frame S'. So the equations 1 become X' equals negative vt', and x equals 0. If we plug these into equations 2, we get our X', which was ax plus bt. In this case, our X' is negative vt' equals 0 plus bt. We solve for t', and we plug this into the t' formula. T' we now know is bt over negative v. C is timesing x, which is 0, so that's 0, plus dt. Both sides have a t, so we get rid of them, And we are left with d equals b over negative v. We know b equals negative av, so b, negative av over negative v, a. d equals a. 3. If the object were a beam of light, Einstein's second postulate demands its speed be c in both frames. So equation 1 becomes x prime equals the speed of the object, whose velocity is c, and its time t prime. The position in x would be then c times t. If we plug these into our equation, which started with x prime equals ax plus bt, in this case we get ct prime equals act plus bt. We will solve for t prime by dividing both sides by c. These c's cancel, these c's cancel, and we get t prime equals at plus b over c t. We will simplify this one step by taking t out and saying a plus b over c, the speed of light, c, not c, our coefficient. We also know that b is negative av, so then we get negative av over c. We can take the a's out as well. So the formula then, taking the a out, is a t 1 minus v over c. And we know that should be equal to cx plus dt. When we plug this in, we know that at times 1 minus vc on one side, and we have that x is actually the speed of light times t plus dt. We can see that we have a t on both sides, so we get rid of all of the t's. We also know that d is a. So if we move that to the other side, we'd have a times 1 minus v over c minus a equals c times the speed of light, c. If we were to substitute these back in, we would get a minus avc minus a, and these two a's cancel. So that cancels and that cancels, and we are left with negative a v over c equals cc. Divide both sides by c, and this becomes c squared. Those are gone, and we are left with c equals negative a v over c squared, where c on the right-hand side is the speed of light. This is a velocity of the speed of light, whereas this c was just a coefficient. And it's technically gone now because we can replace it with a. So altogether, the coefficients simplify down to one unknown coefficient a. And then we can find the Galilean relativity transformation for frame S prime. So we have a is a, b is negative av, c is negative av over c squared, and d equals a. So x prime equals ax minus avt. So we can say that x prime equals a times x minus vt. And we can do the same thing with t prime. We know that t prime equals cx plus dt. So we know then that that is negative avc squared times x plus a times t. We can remove the a, and we will get t minus v over c squared x. Equation 3 tells us that the investigators in the stationary frame S can determine the S prime reference times and positions using these formula. If the investigator knows the stationary position and time measurements and knows the speed of the object, then they can know the position of the object in the S prime frame is some value a, scaling the distance of a moving object. But until we know what the coefficient a is, we cannot finish this evaluation. Before we solve for a, I would like to flip the situation. In case 1, we said that the x prime equals 0 and the x equals vt. But this was just taking from one point of view. We could swap the letters around and change whose perspective we're sitting in which case we could end up writing that x equals 0 and x prime is the one experiencing negative v times t prime. If we were to do it from this point of view, our equation would actually be x equals a x prime plus b t prime. We flip the entire equation around, right? Everything looks the same as the first time. We get 0 over here, but in this time we get a negative a v t prime plus b t prime. We can get rid of the t primes, and we are left with b equals positive a v. In such a case, then, when we plug that back into here, x equals a x prime plus a v t prime, or we can say x equals a x prime plus v t prime. If we solve for a, we would say that a is equal to x over x prime plus v t prime. So we rewrite equations 3 with our known new variables. So we have x prime equals a x minus a v t, as well as t prime equals negative a v c squared x plus a t. If we solve this equation for x, we can then plug that x into our second equation and try to solve this system of linear equations. So if we do that, we end up with ax on one side equals x prime plus avt. Divide both sides by a, and we get x equals x prime plus avt all over a. Plug that into here, and we get negative a vc squared times x prime plus avt all over a plus at. T prime therefore equals, let's see, if we split this into two parts, that is equivalent to having two fractions, both over a. In this case, these two cancel already. And then when we distribute, this a and this a will cancel. And we will be left with then negative vc squared x prime minus, because we're distributing to this next one, and a negative times a positive. The a is still there, because nothing to cancel with. But we get now two v's, so v squared over c squared, times t plus at from rd. Well, we could take an a and a t out of this one side. So we get t prime equals negative v over c squared x prime plus a t. And then we get v squared over c squared. That's minus plus 1. So now what we're actually going to do here is we're going to solve for t just as we had solved for x. All right, because we technically have this x over here, which was x prime over a plus vt. So we want to solve for that t. So we get then the whole thing, let's just move this whole thing over, 1 minus v squared over c squared equals t prime plus v over c squared x prime. So we divide both sides by a times 1 minus v squared over c squared to get t. So then t prime plus v over c squared x prime all over a times 1 minus v squared over c squared. Let's also do it the other way around, where we first start with this one, and we solve for t. So actually, let's put it in the correct values. Negative avcx, should be c squared, plus at. So simple enough, at equals t prime plus avc squared x times both sides by 1 over a, 1 over a, 1 over a. These ones cancel. We get t equals t prime over a plus v over c squared x. Plug that into our x equation. X prime equals ax minus avt. So then we get x prime equals ax minus av times t prime over a plus v over c squared x. If we distribute that through, we get negative, let's go negative v t prime minus a v squared over c squared x. We want to solve for x. That's our pattern. We want x here. So to do that, we have to take the ax out. And on this part here, we get 1. And in this part here, we get minus v squared over c squared. Minus, what's left? vt prime. So x prime plus vt prime equals ax times 1 minus v squared over c squared. Divide both sides. So then we get x equals x prime plus vt over a 1 minus v squared over c squared. So we divide both sides by what's on top here, and we get x over x prime plus vt equals 1 over a times 1 minus v squared over c squared. This is something we saw up here. A equals 1 over a times 1 minus v squared over c squared. So we get rid of this a by putting it over here, and we get a squared We get a squared equals 1 over 1 minus v squared over c squared. Square root both sides. And we are left with the square root of a squared is a. The square root of 1 is 1. And the square root of 1 minus v squared over c squared is the square root of 1 minus v squared over c squared. This is as simple as it gets. So we have found what a equals. Because this a shows up for all of our transformations, we are actually going to define it with a new word. We're going to say gamma is defined by, which is 3 bars, not equals, defined. Gamma is defined to be 1 over the square root of 1 minus v squared over c squared. That's what gamma is. So, given a is gamma, a is equal to gamma, and gamma is defined as 1 over the square root of 1 minus v squared over c squared, our equations, like from equation 3, becomes x prime equals gamma times the Galilean transformation. And x prime equals gamma times t minus v over c squared x. Each consequence involves intervals between a pair of events. Let event 1 have a position in time in frame S. So we will say right here, we have x1, and it is at time 1. And it will have an x1 prime and a t1 prime in frame S prime. Let event 2 have a position in time x2, t2. So after some time, this clock ticks here, and we have time 2, and we can say some value here is x2, and in the frame S prime, we could say x2 prime and t2 prime. Whenever you have a difference, like x2 minus x1, we can just call that the change of x. So in that case then, we have the change of x prime is equal to gamma times the change of x. And the change of t prime is equal to gamma times the change of t.